The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. I think we'll go ahead and get started. Just can you press the little raised hand? I just want to make sure you can hear me, that the audio is working okay. Good. Looks like I can be heard. Okay, excellent. Okay, so we're going to get started. What we're going to talk about today is modeling water treatment using the contaminant transport module. Uh, This is actually going to be a pretty short webinar. The content we have to discuss is pretty straightforward, but it's not used that much. So I just want to make sure that people are aware of this very powerful feature. Um, what we're going to talk about is using the contaminant transport module to simulate water treatment. Now, um, so we're going to assume that you know something about the contaminant transport module. And as you know, that the contaminant transport module is a specialized module that comes with you can purchase separately with GoldSim, and it can be used to move simulate the movement of mass, typically contaminants, through systems. The module is basically going to produce predictions of mass transport rates and concentrations. And the processes that we can simulate are things like just straight mixing, but we can also simulate solubility constraints, and that's going to be important for one of the treatment processes. And other things like sorption, advection, dispersion, and so on. Again, a basic understanding of the CT module is assumed, but I'm going to provide just about a 5 or 10 minute very quick overview for those of you who are not familiar with it, just so you're able to follow the rest of the webinar. So first, we're just going to do a very quick overview of the CT module, just so you understand the features we're talking about. And then we're going to focus on two relatively simple features in the CT module that they can be used to model water treatment processes. One of them is specifying treatment efficiencies, and one of them is specifying solubilities and removing precipitated mass. So treatment efficiency means we want to say 99% of the iron that enters this tank is going to be removed. Specifying a solubility and removing precipitated mass is going to allow us to say within this tank, there's a solubility limit, let's say for iron, it's going to precipitate out, and then we're going to immediately remove the precipitate. So we're going to talk about just these two different mechanisms for us to simulate in a simple way water treatment. I'm also going to mention, but I won't discuss in any detail, a much more complex way that you can model treatment, and that is to actually integrate a geochemical equilibrium code such as Freak-C directly into GoldSim. This is doable. People have done it. It's a very large, complex topic, so I'm just going to mention it at the very end and point you to some resources if that's something you'd really be interested in. So let's just first do a very, very quick overview of the contaminant transport module. So what it does is it adds these specialized elements. Here's the most common specialized elements that you would use, and they're going to allow you to simulate water quality, mass transport of contaminants. It just provides a basic framework, and the complexity model is really determined by the user. It certainly incorporates some basic physics, conservation of mass. You can do decay, and if you have the radionuclide transport model, you can do actually decay and ingrowth, diffusion, partitioning, but it's intentionally very, very flexible. So there's not a lot of other assumptions built into it. One thing that's really important is that it heavily utilizes GoldSim's array capability, so the ability to use, in particular, vectors. And this is because when we're simulating water quality, contaminant transport, we're not just simulating one species, we're usually simulating many species, maybe 10, 20, 30, and we're going to represent these as vectors. So when we build a contaminant transport model, we specify the species, we then specify the transport and storage media um, within the system that we're going to model. This is water, sediment, soil, air, different types of rock. We're then going to talk about the transport pathways. So a transport pathway essentially consists of media. So you might have a transport pathway that represents an aquifer, and it contains water and some kind of solid. Um, a transport pathway may just be a pond or a lake, and it could have water and maybe some sediment in it. Um, we have to define source terms. Where does the mass, how does the mass enter the system? And in some cases, you can actually take it a step further and you can define impacts. So you can convert concentrations. So we're going to compute concentrations. We can convert those to impacts, such as dose or a health risk. This is important for radionuclide transport modeling. It's usually not important for modeling, let's say, metals at a mine. What you really care about there is just the concentration. So when we define species, GoldSim doesn't understand chemistry. That's important to understand. It does understand uh, uh, radioisotopes. So if you were doing a radionuclide transport model, there's an entire database of all the radioisotopes that are built into GoldSim. So it knows who the daughter products are, what the half-lives are. But for a typical model, let's say you're modeling metals or organics moving through a system, it doesn't know any of that. You have to tell GoldSim all the properties. So here I've just specified something called C and something called D, and I've said C decays with a half-life of 5 years, right? Obviously for metals, we're not going to be decaying. Then we're going to define environmental media. And there's two types of media. There's fluids and there's solids. And we'll talk a little about these when I show you the treatment processes. The media are important because the properties of the media are what really controls the behavior of the species in the system. So for example, solubilities in water are a property of the water, a property of the object called water. If you have solids, we can partition between water and the solids, and you're going to have partition coefficients, and they're properties of that particular solid. So those properties are very key in controlling how species move through your system. Transport pathways are really the parts of the system through which we're moving mass. In this webinar, I'm just going to have a very simple transfer pathway. It's going to be a tank where you're basically going to move some water into a tank, and then we're going to have water leave the tank. Obviously, upstream of the tank, in a real system, upstream of the tank, you'll have many pathways, and downstream of the tank, you may have many pathways. We're not going to worry about those other pathways. We're just going to focus on one pathway, the tank itself. When we define a pathway, we have to talk about its geometry, things like its volume, what media it contains. So a tank might just contain water. If I was modeling a lake, I might say that the lake contains water and maybe some sediments. And these transport pathways, you can think of them as transfer functions. We're just moving mass through it. Mass enters the transfer pathway and then leaves the transport pathway. And it could be delayed on the way through. It could be spread out, depending on how the transport pathway is set up. And we build a model by just connecting these transport pathways together. Very straightforward. Here's a model where we have some soil, moves into a shallow aquifer, then to a rock, and then up to a water supply well. And each one of those represents a different transport pathway. And there's processes that move mass from one pathway to another. Most commonly, it'll be advection. We're going to move water from this pathway to this pathway. But we also can have other types of mechanisms. For example, diffusion. Sometimes in some systems, diffusion can be important. And so mass moves between pathways via diffusion. There's 5 types of pathways in GoldSim. We're just going to focus on the cell pathway. It's one of the most common pathways you use in a GoldSim model, and it's certainly how you would represent a tank, a treatment tank, or a system, a treatment plant in your system. Okay, so that's the very quick overview of the CT module. For those of you who are not familiar with the CT module, there's an entire online course that you can take. that's on our website, and it goes into great detail about how the CT module works. Okay, so with that brief background, now we're going to zoom in and we're going to talk about water treatment. How would we want to simulate water treatment? And the way we're going to simulate water treatment is we're going to use these cell pathways. So an important property of cell pathways, they act as mixing cells. So that means the cell pathway has one concentration. It's everything within that pathway is mixed and it has a single concentration. You can put multiple media in a pathway. So you could have, let's say, water in a solid, um, and you could if you had a partition coefficient between the water and the solid, any mass that you put into uh, that mixing cell would instantaneously partition between the water and the solid. It's an instantaneous mixing and equilibration. So that's what a mixing cell is. In a real model, you often have to discretize your model because it's not appropriate to say that this part of the system is completely well mixed. In our case, our mixing cell, our cell pathway is going to represent a tank or an entire plant that we've kind of approximated as a tank. And we are going to assume, yeah, it's all well mixed. It goes in, everything is mixed together. Maybe not instantaneously, but on the time frame of the time step we're dealing with, it's instantaneous. We can impose solubility constraints inside of a cell, and that's going to be very important, and you're going to see that for our second treatment process. Obviously, we can have initial and boundary conditions. Um, from a mathematical viewpoint, we're basically going to a cell network essentially represents a system of differential equations, and GoldSim essentially numerically solves those equations as a network of finite volumes. And again, if you're interested in that, the course talks all about the math behind it. So we're going to start off this by just looking at a very, very simple model. It's got no treatment involved at all, but we're going to build on this model then to show the treatment processes. So in this model, we have a single mixing cell, which represents a tank. We have two upstream mixing cells that are just sources of water. And we have a downstream mixing cell, which is just a sink. It's the rest of the system. And in this simple model, the tank has a certain volume. It starts out at a concentration of 0. There's two inflows. There's inflow from one part of the system, we'll call system 1. It's one mixing cell. In the real world, it would be maybe an entire huge number of cells and pathways. And for that part, we have 0.5 cubic meters per day of water that are leaving each one of these upstream cells and going into the mixing tank. One of the inflows contains 1 gram per cubic meter of iron and zinc, and the other one contains 2 grams per cubic meter of iron and zinc. And then 1 cubic meter per day of water is discharged into the sink. So we have a water balance here, right? So we have 1 cubic meter of water going through the tank. The tank isn't changing volume. So let's just look at that very, very trivial model, and then we're going to basically turn the mixing tank into a treatment tank. So that model just looks like this. And just to kind of go back and talk about how we set this model up, here's our species, and we just have iron and zinc. We do have molecular weights here. We don't really need these in this particular example. I just put them in for completeness. So we just GoldSim doesn't know this. I had to type these in myself. I have something called iron and something called zinc, and I haven't speciated them here. It's just iron and zinc. We have a fluid called water, and it doesn't have any properties that we need to specify. There's no solubility specified here. The solubilities are infinite. All right, here's our 2 upstream cells. All right, and our 2 upstream cells are kind of special cases. We basically have an upstream cell, and we've got what we call a defined concentration. So this is one of the features you can use in GoldSim. You can fix a concentration. So this cell just represents a source, right? It's got a concentration of 1 gram per cubic meter of each species in it, and it's fixed. It's not changing, right? Even though we're flowing water out, the volume stays, it's just a fixed concentration. This guy has a fixed concentration of 2. right? There's nothing fancy happening here. Again, in a real system, you'd have an entire system of pathways upstream here that's leading to our mixing tank. Now let's look at our mixing tank. In our mixing tank, we said has 10 cubic meters of water in it, and it's got two inflows. There's our two inflows from the upstream system 1 and upstream system 2, right? And each one has 0.5 cubic meters per day coming in. And it's going to flow into the sink, and we actually have an outflow here that just says we're going to flow from the mixing tank to the sink at 1 cubic meters per day. So trivial model, right? All GoldSim is going to do is the mixing here. So if I run this model and look at the iron concentrations, for example, and well, we'll look at them both at the same time. Here's the zinc concentrations. Remember, they were the same upstream concentrations. We had 1 gram per cubic meter of iron and zinc in one source, and 2 cubic meters of iron and zinc in the other source, equal flow rates. So we would expect that at steady state, the tank would be halfway in between at 1.55, and it is, right? It didn't get there immediately because the tank started out empty with 0 concentration. It took a little while for it to reach a steady state, right? Just based on the flow rate. And obviously a higher flow rate, if I had more water flowing in and out of the system, it would have reached a steady state quicker. So nothing complicated here at all. This is just our starting point, right, for our system. So now what we're going to do is now we're going to talk about how we can do treatment on that, in that tank. But before I do that, I just want to real quickly just show you the actual equation GoldSim is solving there. So by setting up the model that the way I did, we have a differential equation that says the rate of change of mass in the tank. There's actually 2 equations, one for each species, is Q1, the flow coming in times the concentration coming in, plus Q2, the flow coming in from the other source, times the concentration coming in, minus the flow rate leaving the tank, divided times the mass in the tank divided by the volume of the tank. The volume of the tank in this case is constant, and this is the differential equation we're solving. Right? We actually have 2, one for each species, but they're uncoupled because the species are not they're not related to each other at all. So that's basically the math that we're solving here. It's not rocket science at all. Okay, so now let's try to treat the water that's entering that mixing tank. And as I said, there's 2 simple ways to do this, and that says one is to define a treatment efficiency. And this represents the fraction of the incoming mass that is removed from the system. So what we're saying is we have, let's say, 100 grams per day entering the tank. If I define a treatment efficiency of 0.9, 90 grams per day will be removed from the tank. That's essentially what we're doing. That's what a treatment efficiency does. The second approach, we can say we're going to define some solubilities of the species in the tank. And so the tank will be at that concentration. Mass is going to drop out of solution, and we're going to instantaneously remove that precipitated mass from the system. So many treatment processes, this is how they actually work. And so depending on what you're trying to accomplish, that may be a better approach to modeling treatment than the first approach. And as I said, there's this third approach in which we can link to Freak-C or a similar tool. We'll talk about that just a little bit. Okay, so let's first look at the first approach, and this is the defining treatment efficiencies. So we have the exact same system here that I just showed you. The difference here is now I'm going to define a treatment efficiency within the treatment tank, right? And we're going to basically set up a system that looks like this. We're going to add another mixing cell over here, which is where we're putting the mass that we're removing. And essentially what's going to happen is we have X grams per day coming from this source. We have Y grams per day coming from this source. And what we're going to do is we're going to send X plus Y times the treatment efficiency to the sink. And the rest of the mass is going to move on to the downstream system. that is what a treatment efficiency is going to look like. So let's look at that model. And so this model looks like this. There's nothing different in terms of our species or water. They're just like the other one, okay? The difference we have here is I have a treatment efficiency defined, and you see what I've done here is it's a vector, right? Because I have two species, so I have to define a treatment efficiency for both species. I could define 0, in which case there is nothing removed, right? There is no treatment. Here I've said iron has a treatment efficiency of 0.9 and zinc has a treatment efficiency of 0.99. That's what I've said, right? In my treatment tank, let's go to the treatment tank. We still have the same inflows coming in. It's no different than what I showed you before. And we have this outflow right here. This right here, we're flowing water at 1 cubic meter per day to the downstream system. That isn't changed at all. But what we've added is a second type of outflow here. All right, and it's a special type of outflow. You see the medium, there is no medium specified. It literally says fraction of inflows. So what does that mean? Well, let's recreate that. I'm going to go ahead and delete that guy, right? And now I'm going to add him, right? I'm going to add a new outflow that represents the treatment process. And I'm going to link to this thing called sink removed mass. I want to put that mass somewhere, right? I want to keep track of the mass that I have to put it somewhere. And it also allows me to keep track of the mass that I've removed. So I'm going to say sink removed mass. And now usually when you create a link like this, this would typically be an advective connection, right? But we're going to say, no, I don't want advection. That's not what I'm doing here. So instead of where it says water, if I drop this down, you're actually going to see some other possibilities here. And the one we're going to pick is called fraction of inflows, because what we're going to say is we're going to remove a certain fraction of all the mass inflows that's coming in. So this treatment link is called fraction of inflows. I hit OK, and now here I have to say, what is the fraction I'm removing, right? Well, that's the treatment efficiency, right? This has to be a fraction, it's dimensionless. It's the fraction of each species of the incoming inflows, mass inflows that you're removing. So I'm just going to link it to that treatment efficiency right here, all right? And that's it, we're done, right? And now I'm going to, if I run this model, right, and I look at the concentration of iron, this is the concentration of iron in the treatment tank. It would also be the concentration of iron leaving the treatment tank. You can see it's much lower, right? It's not 1.5 anymore. In fact, it's 0.15. Well, we said that we were going to remove 90% of the mass that enters, and that's exactly what we're doing, right? If I look at the concentration of zinc, you can see here it's 0.015. We've removed 99% of the mass of the zinc, right? And so what's going downstream is only 1% of what was coming into the tank. What's going downstream of iron is 10% of what was coming into the tank. That's all we've done. Very, very little simple representation of the treatment process. And of course, we can always, let me save the histories here. I didn't save the histories of the mass. So this is the mass that we removed from the system, right? We still have a mass balance. And you can see we removed more zinc than iron. Because it had a 99% efficiency, this only had a 90% efficiency. So that's the mass that's been removed and put somewhere else. And so that's all we've done here. It's a very, very simple process, and all you need to do is say, how effective is this plant, right? And the guy says, oh yeah, we can remove 90% of the copper, right? We can remove 95% of the zinc, whatever, right? Couple comments here, right? the treatment efficiency, I just put in as a constant, but it doesn't have to be a constant, right? In fact, they may tell you that the treatment efficiency is a function of the concentration that's entering, right? So you could make this a function, right, if you wanted to. It could be a function of other things. Maybe it's a function of, you know, other things that are going on in the system. Um, this doesn't have to be a constant, right? The treatment efficiency can be responsive to other things. There is one thing that's really important to understand, and those of you who are not familiar with the CT module, you may not be able to follow this. Those of you who have used the CT module, um, uh, you'll see this, and it's a very, very important point. So remember, just to summarize what we did, we had an existing outflow that represents the treated water leaving the tank. So that's the same as you'd always do. We have a new outflow that represents this treatment process, right? But there's a very, very important point here, okay? We can only treat incoming flows that are coming in as normal links. What do I mean by that? Well, let's go back to the model. Okay, if I'm going to go at this is my my original inflow into the system, and I have an outflow from this upstream to the treatment tank of 0.5. I'm going to go ahead and delete that, and I'm going to recreate it. Usually, when you create a flow rate, right? So I want to go into my treatment tank. See, okay, it's a advective link into the treatment tank. The default link says coupled. Okay, if you leave this as coupled, this water will not be treated. For mathematical reasons, we can't treat this water. You mark this as a normal link, right? You can read in the documentation how this affects the model. It wouldn't be noticeable in most cases. It's not something that you have to worry about for advective systems. But these have to be normal links. You'll notice that both of these guys are normal links, and they have to be. He says link type is normal. If they're not a normal link, if I set both of these to coupled, right, you wouldn't have any treatment at all. Water there would be no mass removed. So that's a very key point when you're using a treatment efficiency. Everything coming in has to be coming in as a normal link, right? Straightforward to do, but you have to remember to do that. Okay, now I want to talk about the second treatment process that we can simulate. And in this case, what we're going to do is we're going to define solubilities for species in the treatment tank, and only in the treatment tank. So the rest of the model either has an infinite solubility or it could have some other solubility, but the treatment tank has a special solubility. So we're going to have to specify a model in which the solubility varies depending where you are, okay? And in this case, it's going to look similar, right? But our model is going to look like this. We're going to have mass coming in. The mass leaving is going to be the flow rate leaving times the solubility limit, because we've set a solubility limit here, right? That's the mass that's leaving. A whole bunch of stuff is going to precipitate out, and we're going to immediately flush that out of the system and force it to go into the sink over here. So that's what we're going to do with this type of approach for doing a treatment process. So let's open that model and look at it. So that model, the structure looks similar, but we have to go up here to our materials because there's a very important difference here. So I now need to specify solubilities. So this is kind of an advanced feature. The problem is that the issue we have here is we have water in GoldSim. Water, this is what's called a reference fluid, right? It's in all of your environmental models, water is the reference fluid, all right? But now we want kind of a different, we still want water to exist in other parts of the system. We're going to say there's water going through the tank, but this water has slightly different properties, all right? So the way we're going to do that is we can't just copy the water element or create a different fluid and put it there. We're going to do something called cloning an element, which some of you who have played with GoldSim a lot have done, but we're going to create a clone of this element, right? And the way you create a clone, you literally right click on it and you say clone this element. It's going to have the exact same name, right? So if I'm going to clone an element, I only can clone an element if if I'm uh, if I have a localized container. So here you say I have a localized container called treatment, and what I did is I cloned that water element to right there. So a clone, basically, they have all the same properties. And you can say, well, wait a second, if they have all the same properties, they're going to have the same solubility. Because the way this model is going to work is everything else in the system, obviously you'll have a lot more in a real model downstream and upstream, they're going to be looking at this water for its properties. That's who they're linked to. This guy is going to link to this water, okay? But you say, well, if they have all the same properties, how are they different? The way they're different is if you look at this, it just says solubilities. What it says is go use the thing called solubilities, right? But the solubility is different in each of those locations. So in this case, the water links to this solubility. And in this case, the water links to this solubility. The solubilities are different. So I now have created a system in which water exists in both cases, but it's slightly different flavor because it's got different properties. The entire model has negative solubilities. Those of you who have used CT, a negative solubility means I'm infinitely soluble. It doesn't have to be, by the way. It could be any solubility. This guy's got solubility specified of 0.1 milligram per liter and 0.01 milligram per liter, right? So this treatment tank, that's the solubilities that are going to be applied there and only there. Now, in a complicated model, you can have different solubilities all over the place. Usually you don't. Usually you don't, but you could, right? And in this case, you certainly have to, because the whole process here is we're saying the treatment, the treatment plant had, we're modifying something. We're adding something, lime or something, or we're adjusting the pH to change the solubility. So that's what we've done here. All we've done is we've got a solubility assigned to the water. All right. If we then go back and then we look at that treatment tank, once again, we've got an outflow that just goes downstream, just like we had before. But now we've got another outflow that's a little bit different. Before we use this as the fraction of inflows, let's delete this and recreate them. And I'm going to say I want to remove mass to this thing called sink removed mass. And again, I don't want it to be an effective connection. I don't want it to move water. I want it to be a specialized connection. And it's going to be the precipitate transfer rate. This is the rate, it's a fractional rate at which we're flushing precipitate out of the system, okay? Once I do that, I have to put in a rate, a fractional rate. In most cases, you just want to put in a big number, right? You're saying, I'm going to flush it all out of the system real quickly. As soon as it precipitates, boom, it gets removed, right? Theoretically, you can say, well, it doesn't get removed that quickly. But no, we're going to basically just flush it completely out of the system really quickly. So it's going to flush out 100 is plenty quickly. So that's all I've done here, right? And now if I run this model, and now let's look at the iron concentrations, you'll see that the iron concentrations are constant. Well, what happened is, well, we immediately at this point hit the solubility limit of 0.1. And that's the concentration of iron in the tank. It's also the concentration of iron leaving the tank, right? If we look at zinc, we specified a concentration of a solubility of 0.01. We immediately apply that solubility inside the tank, and it reaches that very quickly as soon as we put in a little bit of mass. And that's the concentration leaving the tank, right? So the concentration leaving the tank going downstream it's leaving at the solubility limit. because we have low solubility limits and there's a lot of mass in the system. Obviously, if you didn't put enough mass in the system, you would never reach the solubility limit, and it would just be moving through the system. But in this case, we're precipitating mass out of the system, and then we're moving that mass here. And this is the sludge, basically the precipitated mass that we're moving. And there's the mass that we removed from the system. We removed more zinc than iron because zinc had a lower solubility limit, right? And so we flushed more zinc out of the system. So two different ways to tackle treatment. Both of them are very, very simple, right? To kind of summarize that approach, what we're really doing is we have to define the solubilities in the tank locally by cloning the fluid element there, right? And defining a different set of solubilities there than we would. In order to do that, by the way, this has to be a localized container, right? Because it's called water, so it has to be. And it's called water, and I have two elements here that have the same name. There's a water and a solubilities here, and there's a water and a solubilities here. So basically, I have to localize one of those guys in order for this to work. The one we want to localize is this guy, because if we localize this guy, these guys wouldn't see any water. They couldn't find water anywhere, right? And they need water. They need to be saying, well, what's the properties of water? And so they're hooking into that water. Again, we define our original outflow, and then we have a new outflow that represents our treatment process, and it's this precipitate transfer rate instead of an actual medium like water. And then we set the rate, the transfer rate, to a high number so that any precipitated mass is flushed out of the system very, very, very rapidly. So that's those two approaches. Let me just very, very briefly just mention this approach number 3, and this is integrating the actual chemical processes into GoldSim. Here's an example where we're actually simulating the inside of the facility. We've got a lime tank and an aeration tank and a pH adjustment tank, and all of these things we have to have some geochemistry going on. This particular model doesn't actually link directly to FreakC. It just has a whole bunch of lookup tables that were created using FreakC. There's a whole bunch of different ways to approach this. You will see on our in our support help desk, there is an article that describes different ways of tackling this, put together by Ted Erie, who's a geochemist, and ranging from a fairly simple approach to kind of an intermediate approach where we're running FreakC and using lookup tables, to actually linking a geochemical code like FreakC directly into GoldSim and calling it every time step. And you can go to this, and if you're interested in pursuing this, you can actually kind of walk through that article and download the models and the various examples. But you really want to think hard about this, right? Can you accomplish what you want to do by just using one of these two simple treatment processes, right? I mean, maybe you just go to the guy who's running the treatment plant and ask him, can I describe this as a treatment efficiency? He says, oh yeah, we're going to remove X% of the zinc, but it's a function of concentration. So maybe I need to. Maybe he gives you something more complicated than just the constant. Or maybe you can say, yeah, we're just going to precipitate all this, and we're going to assume this solubility limit, and that's what we're going to have leaving the facility. We're going to have this solubility leaving the treatment plant, and everything else is going to drop out as a sludge that we're going to pull out. So you might be able to get away with that. So you should really think hard about that before moving to a way. I mean, this approach is way more complicated if you were to link FreakC into it. Just enormously, orders of magnitude more complicated. You're going to have to understand the geochemical code. You're going to have to link it dynamically to GoldSim. You're going to have to do some programming to do that. So it's not something you want to take lightly. Whereas the two methods I just showed you, as you saw, are pretty simple. You can set them up very quickly. Obviously, you need to know what those treatment efficiencies are and what the solubilities are going to be. But if you know that, if you can be given that information, it's very simple to set up in your model. So summary, there's our two simple approaches, and we have our more complex approach. Um, uh, we will be posting probably tomorrow this webinar, a recording of it, this PowerPoint presentation, as well as the models I just showed you. So you can play around with them for yourself. And if you have any questions, as always, we're happy to discuss questions about these webinars. Send them to our help desk. Just go onto the help desk and say, can you explain why this works, or how I should take this, and we're happy to answer those questions. So with that, I think we'll wrap it up. Unless somebody has some questions, you can type in. We have some time, and I can answer a few questions if anybody has any questions. I'll wait a minute or two here. Again, if it's a complex question, it might be better just to send us something via our website, so we can go into more detail. So it looks like there isn't. So great, thanks for joining us, and have a good day. And we will have this posted probably by tomorrow. Take care.